It is time to talk lasers, people. And this is chapter 19. It's not chapter 9, it's chapter 19. Sorry about that. Low level laser therapy is the name of our chapter. It's therapeutic lasers, it's soft lasers, it's cold lasers, or whatever you want to talk about. But therapeutic lasers is probably the most common one. And who knew that going to a Rihanna concert could be therapeutic? I mean, last time I went, all these lasers coming at me, my injuries got healed, my pain went away. I felt really good for some reason. I don't know why. All right, your book starts off talking about under the therapeutic laser section. It does mention what laser stands for. I'm not going to make you regurgitate that. I don't know if that really holds any value other than when you look at it, it's amplifying simulated emission of radiation. So that does tell you how it's produced. When we talk about, I'm not going to make you memorize those, but when we talk about how the laser is produced, this becomes a little bit more, I don't know, coherent, or it kind of clicks, like, oh, okay, that's why they call it what they call it. Most people think of lasers as, or a lot of times people think of lasers as the ones that can cut through things or burn things or melt things. Those are the hot and hard lasers. That's not what we're talking about. Ours are going to be the lower power stuff, soft, therapeutic. Sometimes they're called cold lasers. You'll also hear, like our book calls it, the low level laser therapy. That's what this LLT is. You might see it called low power, for the P, put the P in there. Low power laser therapy. You're going to have a lot of these terms that come out at you. But ultimately what we're looking at is we're using this photon as our energy source. And so in that book, right in your book, right after it talks about what laser stands for, it mentions the photon as this unit of light energy that we're using, that we're applying to the body, and we're using to create our physiologic effect. We'll talk about the infrared, or the light spectrum, and the red area, the infrared area, again here coming up. I'm going to throw another term out at you, though, and this is not in your book. This is a real term: photobiomodulation. Don't look like Jim. That's what I look like when I first. What did you just say? Photobiomodulation. This is there's associations for everything. I just put this on there because I thought it was interesting that there's an actual photobiomodulation association. Whew. That's a lot of words, man. What the heck is? I don't know if I've cleared this up any bit. Obviously, you can see. All right, we're using lasers, LEDs, lights, some kind of stuff. Here's the meat of it. And you see, all right, non-thermal. I get that. Endogenous. That's things that are within the body. Chromophores are the ones in the body, right? So these chromophores that are in the body. There's photophysical, photochemical. So there's some kind of effect, physical and chemical effects that are generated from our photons, from our photon energy, and we're going to basically affect the biologic or the physiologic stuff. And these are the outcomes that we get. And so ultimately, when you break it down, it's not really super hard. It's a fancy word. It'll make you sound smart. And hey, we're going to be doing some photobiomodulation today. What the hell is that? Oh, that's just laser, right? It's just light therapy, right? So that's all it is. But hopefully that clears it up. This is a good search term if you ever are. You're not going to have to do an abstract, but if you're ever searching for laser information and studies, photobiomodulation is a good search term that you can use to do that. This little diagram right here, in fact, I'll make it bigger, is a common diagram. You'll see variations of this diagram in a number of stuff. In fact, on our portal page, I have this part, this bottom part is on there, but it's a little bit better because it has little explanations on it. But ultimately, the chromophore, this cytochrome oxidase, which is chilling in the mitochondria, powerhouse of the cell, gets exposed to this light energy, these photons, and it generates the production of ATP. That sounds pretty cool. Nitrous oxide. What the hell does that mean? Reactive oxygen species. So these are the three things right here that are most commonly talked about as causing the physiologic effects that we're looking for from lasers. Before we get talking too much on the physiologic effects, I do want to talk a little bit about how this laser is produced. It's not super important to your understanding of the laser, because a lot of people go, look, I push a button, a red laser comes out, or a light comes out. Who cares what goes on inside? I'm with you a little bit, but we talked about the piezoelectric effect for ultrasound. We talked about radio waves for diathermy. So just briefly, I want to talk a little bit about how this laser is produced inside our little laser machinery. And ultimately, we need to produce light energy. We need to produce waves of light coming out at a specific wavelength. And we start with what we call this gain medium, or this substance. And you'll see here on the next slide, the next couple of slides, it's either going to be this gallium arsenide or helium neon, right? The substance, those are the more common ones. The substance is not as important as just there's this medium that once we have it inside our little laser machinery, we apply some electricity or some power to it. In our case, it's going to be some form of electricity. And once we do, then it starts to release the photons. So we get these little photons that release at specific wavelengths. That's what you see, these little squigglies. Look at these little squigglies in here. The other thing that's involved are these kind of reflective mirrors that cause these little photons, these little wavelengths of light energy, to start going back and forth and bouncing back and forth. And as they bounce back and forth, they amplify, and they get, the wavelength grows until they get to a specific wavelength where it's partially reflective because there's an opening. And if we get to the specific size of wavelength, then it shoots out as that beam of light. And that's ultimately what we have. On, I don't know what page it is. It's table 19-2 in your book. I'm looking for it right now. Oh, it's on page 368, sorry. Talks about the different types of therapeutic lasers. I picked the two, the helium neon and the gallium arsenide. You can see kind of the differences. It's in the chart. It's in my thing here, that the penetration, we can see this, right? We can see the red beam, a little bit less of a penetration. So when we talk about some of these visible lasers that we have, a lot less power as opposed to the infrared. So this is going to be an infrared laser. So you have our wavelength is a little bit longer, right? And so it's going to go deeper. Longer wavelengths, going to spend more time going deeper into the tissue as we go. And so what we're looking at is that electromagnetic spectrum. And we had this visible, we have the infrared, the non-visible, and this little short, small, visible spectrum. This is in nanometers. And so you can see whenever any kind of light is within a 400 to about a 700 nanometer range, we can see it. And if it's out of that range, we cannot see it. So based on the wavelengths I just gave you, there was like one that was like 630 something, right? Somewhere right in here in this red area. And the other one was past here, 8 to 905, right? So you're in this, that's kind of the wavelengths. That's why we can't see them. When we can see these lasers, there's a couple terms that you should be aware of. Coherence is that when a laser is coherent, you have all these photons at the same wavelength in the same phase. When that happens, you get the laser, right? So lasers have coherent light. This is just white light from the sun or from our lights in the lab. It's all these different wavelengths coming out. So we don't really see a beam of light. We just see light. When we see the laser pointer, that's all that light coming out is all in phase. So they're all the same wavelength. It all comes out as that specific color. And that's what will give you that monochromaticity. Whew. Yeah, I gotta practice that too. When we have divergence, it's, we have minimal divergence. If it's coherent, we have minimal divergence. So it's culminated into this beam of light. So when a laser actually reaches the skin or comes in contact with the skin, you have a couple different options. It depends on the laser, right? You can have a thermal where we can actually cut open things and use it in surgical procedures. We can actually destroy tissue if we had. But most of the times when we're using it, the therapeutic side, we want a physiologic response. And so what we're looking for, this is that bottom portion of that other diagram that I just showed you. We're looking for this chemical response right here. We're going to target the mitochondria. Specifically, what's in there is this cytochrome C oxidase. And that's going to generate, we have reactive oxygen species, here's our nitrous oxide, and here's our ATP production, which creates this physiologic effect. And again, I made it a little bit bigger for you. Now, I want to remind you a little bit about our previous conversations about absorption, transmission, reflection, that kind of stuff, because the light that we apply is definitely can be affected by the tissues that it comes in contact with, and it is also dependent on the wavelength that it is. And so here's that wavelength, or here's that wavelength here, the difference. That first gallium arsenide laser that I talked about is right in this range here, not a very deep laser, as opposed to when you get up here in this infrared area, then it's going to go a lot deeper. So I wouldn't worry too much about the specific ones of the blue laser. But definitely visible red and near infrared is what we're going to focus on for our therapeutic conditions. Now, as these wavelengths go down, as this laser kind of comes down and goes into the skin, it's being absorbed, in different depths based on the wavelengths. As it comes in contact with different structures, like the previous slide, it can be scattered, or it can reflect, or it can be absorbed. The more that this laser, this light energy, comes in contact with chromophores, or things that will absorb the energy, then it starts to become absorbed, and it dissipates, and it won't penetrate any deeper. Things that usually we're going, like I mentioned, we're targeting the cytochrome in that mitochondria. There's other areas there's other chromophores that are there that will actually absorb the light energy as well. Things like melanin, red blood cells, the water in our bodies. And so ultimately, a lot of the lasers try to keep it in this range right here, because you get the least absorption from these structures, and we get the most absorption from our targeted structures, that mitochondria and that cytochrome oxidase C. There's different ways of delivering this for there's always continuous, and then there's pulsed, right? So the continuous wave, you can see, is just a continuous stream of light energy or laser. The super pulsed, you have these super bursts of laser energy of that kind of stuff. This is, we're talking nanometers and now nanoseconds, right? These little pulses in nanoseconds, you get minimal heating, and that's kind of what these cold lasers are about. So as we keep going here, let me click this. I want to talk about the power and dosage. Page 368 talks about the dosage. We have a new term called joules. And basically, this gives us, joules is a representation of how much power per second is delivered. So it's almost like a speed kind of thing. It's joules gives us just the amount of watts per second, and it's still calculated based on the size of whatever the laser is coming out. So this is obviously a smaller head of the laser. This is a bigger head of the laser. And so that's where you get this centimeter squared type situation. The time that you set, typically you don't really set time, because most of these machines will do the calculations for you. On page 368, you see a number of calculations. In fact, I put one up there. Right there, it talks about, look, if you want to deliver 5 joules per centimeter squared, if that's the amount of power you want to, of laser energy you want to do, and your machine, say you got this machine right here, will crank out 1 milliwatt per square centimeter. Okay, then you can see the actual calculations in your book if you're really interested in multiplications and order of operations. But ultimately, that comes out to 50 seconds. So if we look at a realistic dosage, right? So if we're talking about how much dose do we want to deliver, if we want to deliver 30 joules per centimeter squared, then, and we're using this machine right here, then it ends up being about 300 seconds or 5 minutes. If we had a different machine, so if I had a machine that gave out 2 watts per centimeter squared, then this would go down. This would probably go down to 25. This would go down to 2.5 minutes. So it adjusts. The machine itself will do the calculation. So there's rarely any time that you actually, unless you know a lot more about lasers than the average person, and you want to put your time in directly. Manually, most of the time the machines will just have a set time that will come based on the dosage. When I talk about dosage and laser, it always makes me think of this analogy, right? So we're talking about a medicine that we want to deliver. We're going to deliver this laser. It's just like taking different strengths of ibuprofen. If you have your normal over the counter and I want to take 800 milligrams, right? These all come in 200 milligram pills, so I'm going to have to take 4 pills to get my 800 milligram, the dose, right? That's what I want. If I have this kind of laser or this kind of pill, this is a bigger pill, comes in a prescription now, but now I only have to take 1 pill because it comes in this 800 milligram dose. So hopefully the dose concept, and we can talk about it a little more in class, but hopefully this dose concept is understandable, that it's just based on the type of laser that you have, and just like it's based on the type of pill that you have. Am I going to take 3 pills, 4 pills? Am I going to take 1 pill, kind of thing? The other thing that this talks about, and this is on page 369, that figure 19-3 has that nice little flow graph, and then the same thing on page 368, right underneath the dosage part, it talks about this Schultz law, this biphasic response. So we have to have enough energy to stimulate if we want to stimulate stuff. As we get into the higher doses, we start to get an inhibiting effect. If we get too much, we start to have an inhibitory effect. Sometimes we want inhibitory, right? So if we want pain relief, if we want to inhibit pain neural transmission, then we might want a higher dose. If we want to stimulate the tissue repair and some of those other effects that we've already talked about, we might want a lower dose. So it depends on what our intended effects are. So when I talk about the biphasic response, I'm not going to ask you about the Schultz law. I mean, it's pretty straightforward that you need, if you don't have enough dosage or enough energy to stimulate a response, then you won't get a response. It's pretty straightforward. What I'm talking about, what I want you guys to focus on, is this biphasic response, and that lower doses give you this stimulatory effect, and the longer we apply it, or the more power, right, the more the doses that we apply, we start to get into a inhibitory effect, and we can get and so you can get both, right? If you do it for a long enough period of time. This is pretty cool. You get a low dose, we get a little bit of stimulation. If we apply that same dose for a long period of time, we start to get some inhibitory as well. And then this just gives you the super high power. The more power that you deliver, the more inhibitory that you can get. So there's 2 different, basically opposite responses. That's where you get this biphasic response. Don't confuse it with the biphasic wavelength in E-stim. This is just a biphasic response that we do. All right. When we apply laser, right? Ultimately, what we're going to do is, based on the clinical application or based on what kind of tissue we're treating, we're going to set our power or our doses. This should really say dosage right here. We're going to set the dose that we want to deliver, and the machine is going to calculate the time that it takes to do that. And so it'll come up with that. Some of them, a lot of times, are just preset. You push the button, it comes on for a preset 5 minutes, and it adjusts as it goes. As we apply this, we're going to direct this energy in a perpendicular, format to the tissue we're trying to do. And then there's these different techniques that are available. And now these are in your book, but we'll talk about these in class. Most of the time we use gridding, where we just go to one spot here, spend a little time, the next spot, spend a little time, next spot, spend a little time. That's like kind of the grid type situation. Scanning is just like it sounds, you're kind of moving it over the area. But we'll talk a little bit more about it in class. It's in the book if you don't want to wait until we talk about it in class. The table 19-3 gives you some of the dosing protocols, just general, right? So just some general protocols that you can get. That's where I got my 30 joules per centimeter squared. This is the one area that you need to go through because we didn't talk. I'll talk a little bit about it in class, but we really didn't talk about it in this. The safety, the classification of these different lasers. And so when you interact with lasers, you'll talk about, oh, this is a class 3 laser. This is a class 4 laser. These are different types of lasers. And so I want you to look at that table 19-1 on page 366. Make sure you have an idea of that. All right, I'm not going to play that video. Maybe I'll play it in class. This is the picture that I have on the portal site. I want you to look at this because this encapsulates everything I want you to know about here. The chromophore here, we're talking cytochrome C oxidase in the mitochondria. Here's what it does. It goes boom ATP, boom reactive oxygen species, boom nitrous oxide. Here's what they do. So this is kind of this is the step by step. All of this information on here is gravy, or it's good, or gold maybe. Whatever you want to use to say this is good stuff. So please, please, please know this like it's the back of your finger, maybe your hand, I don't know. All right, the final one starting on page 370, it has all these different, and I'm not going to talk about too much on this, so I'm just going to put them all up here. You have them in your notes. You can read them in the text. Page 370 has all these different sections on the clinical uses and how basically how a laser will do wound healing, how it will reduce scar tissue, how it gets rid of pain, that kind of stuff. So, all right, I'm gonna cut this short, and I know it's a lot of information in a short amount of time, but we will have some time in class to go over this. So, and if you've never played with a laser and a cat, I don't think you're missing out on some fun. Yeah, so I'll leave you with that.